And we know from the very definition of a minimal generating set that we can generate that. Right? These are just integers. They're just integer powers. So for every element that belongs to A, it will have this form, and we can generate it from the MGS. Okay? There are, we know we can do that. And this would be the element, for a given R, whatever, for these R's, whatever they are, this would be the element here that maps to it. Okay? So whatever these R's are, you just put them in here, and you'll get a corresponding element here that maps to this. Okay? All right. So surjection. Now, how about injection? Well, remember the proof, and we've used this kind of thing several times. If the size of the two sets are equal, then if it's surjective, therefore it's injective. So let's use that. Now, I was saying a bit earlier, getting quite hot here. It's about 35 centigrade. Sweating. So this, mentioned the size of this is 2 to the n. So we need to show that the size of this is also 2 to the n. Alright, well, from an earlier theorem, in fact just the previous theorem that took us about half an hour to prove, can you remember these powers here take the form 0 or 1? Remember that? Alright, so each of these integers here is either 0 or 1. Okay? So how many elements, how many possible elements does this minimum generating set, how many different elements can it generate? Well, you have two choices here, right? It's 0 or 1. And similarly here, for all of them, they're 0 or 1. And you have n of these. So two choices times two choices, times, time. So 2 by 2 by 2 n times, that's 2 to the n. So the size of, the number of ways you can have this element here is 2 to the n also. So therefore, the size of these two groups, is the same, and we've already proved surjective, and therefore, from that earlier theorem, we know it's injective. And now we know that it's surjective and injective, therefore it's bijective. Okay, so well formed, we've now proved that it's bijective. Now we have to prove that f of mn thing. Alright, so in general, like f of mn, you have to show that that's the same as f of m, f of n, that kind of thing. That's sort of general form. Now if we translate that into our problem, what's m? It will be of this form, right? We take two elements of our starting set of this, so it will be of this form. So so f of m, now m will be like one of these, so r1, comma, r2, comma, dot dot dot, r the n, right, and then there's a binary operation here. Now that binary, what's the binary operator for these residue classes? Well, it's plus. Okay, so the binary operator here, so there'll be plus, and then you'll have another term of this form. So we'll just call it S. It's quite general. So S1, comma, S2, dot dot dot, S of n. All right. Now we can rewrite that a little. Now, from basic theory of, sweating like a pig. basic theory of residue classes is these add. Residue classes behave very much like integers, right? So you can add them, you multiply them, and subtract them, and so on. So you can just rewrite this as f of, you just add them, okay? So this will be R1 plus S1. So R2 plus S2. Dot 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 Rn plus S of n. Alright? Okay, now f of this, look at this form and look at this form. Okay? Now instead of having R1, here we have R1 plus S1. Okay? Now this becomes this, that's our hypothesis for the mapping function, our f. So now since we've got R1 plus S1 here, this will become R1 plus S1, right? So we translate this into this form because you know, we're mapping this member from D. All right, so this will then just become A to the R1 plus S1. So times A2 R2 plus S2 dot 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 A to the N R to the N plus S to the N. All right. Now remember, it's an abelian group. Well, let's rewrite this up a little. So this is A1 to the R1 times A1 to the S1. Just rewriting the exponents a little. A2 to the R2, A2 to the S2, dot dot dot, A to the N, R to the N, A to the N, S to the N. Now, okay, now comes a useful trick. What I want to bring all these R terms together. So I want these to end up here, and I want this one to end up here. In other words, I want all the R terms to be like on the left-hand side, and I want all my S terms to be on the right-hand side of the product. Now, you may ask, well, why? Why do you want to do that? Well, you'll see in a minute. But look, these are just elements, right? What elements? They are elements from your minimal generating set. Now, they're just elements of an abelian group. Okay, so like I can have you know, I can split this up into A1, S1 times. Okay, and I can split this one up into A2, R2 times. So I'll have an A1. If I do that, I'll have an A1, like the last A1, and the first A2. So in here I'll have like an A1, A2. Now I can reverse that because it's an abelian group, right? So I can have A2, A1. Now by doing that many times, I can shift these A2s to here and shift these A1s to here. So I can swap over this whole block, right? It'll take many steps, but I can do it in principle, right? So generalizing that idea, I can end up with the following: A1, R1, A2, R2, dot dot dot, A, N, R to the N. So I take all my ARs, well, the AI, and then bring all these ones this side. So that will be A1S1, A2S2, dot dot dot, ANS of n. Right? I'm just shuffling the order of these elements, and I can do that because the group is abelian. Right? I can take any two next to each other. I can swap them around, and so, like for example, say I had A, B, C. It's the product of three elements, and they're all abelian. Well, I can move this C to here, right? How do I do that? Well, it's ACB, right? And that's CAB, right? What have I done here? I've commuted B and C in there, and then I commute A and C and get CA. So I've moved this C to the left. So I can do that kind of thing, with this in general. But look, this here and this here is what? This is f of r, right? This is this. So I can rewrite this as f of A1, sorry, R1, comma, R2, comma, Rn, times, these are just the times f of S1, comma, S2, dot, 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 S of n. Okay? And there it is. That's what I wanted to prove. It's because that in effect, that's your f of m. So there's just one element of your set D, right? And that's the other, that's your n, if you like. So n corresponds to that, and n corresponds to that. So, and this is effectively your f of mn, this, right? And that equals that. So you proved it. Alright, so that's the proof of 3.8. Now look, have a look at this. This is a special case of a more general case. So now we're talking about theorem 39, and Barnard does not give a proof for it. So it's just like a taste, a feeling of what's coming, say first year Masters M1 in finite group theory, especially talking about finite abelian groups. Okay, so the theorem says the following: instead of just having twos here, the two here is your that's the order of your groups. Sorry, your elements in your abelian group. So this is a more general case, right? This would be a special case of this. Now these. So you have an abelian group. You know its order. Let's say its order is I don't know, n, big N. Okay, and these p's here, they're prime numbers. Okay, and these r's here are just